A production database, 300,000 records, silently corrupted overnight. No action was thrown. No alert fired. The AI agent did exactly what its prompt told it to do, and that was precisely the problem. The team had spent 2 weeks perfecting that prompt. They added constraints, they added examples, they added chain-of-thought instructions. Every iteration made the prompt smarter. But nobody built a fence around what the agent was allowed to touch. Here is the uncomfortable truth that the AI tooling industry does not want to say out loud. In 2026, the more carefully you craft your prompt, the more confidently your agent will walk straight into the wrong place. Prompt refinement gives an agent better aim. But if you haven't defined the target boundary, better aim just means faster damage. By the end of this lecture, you will know exactly what that fence is called, how to build it, and why the engineers shipping AI at scale figured this out long before the rest of us. The answer is not a better prompt, and that realization changes everything. Now consider the opposite end of the spectrum. Stripe, one of the most operationally disciplined engineering organizations in the world. They are merging 1,300 AI-generated pull requests every single week. Not 13, not 130, 1,300. At that volume, you cannot babysit prompts. You cannot review every output manually. You cannot rely on an AI being well instructed. What Stripe built instead is a control layer, a harness, that wraps around every agent invocation. The harness defines what repositories an agent can see, what file paths it can write to, what test gates it must pass before a PR is even created. The prompt inside that harness can be relatively, because the harness is doing the heavy lifting of constraining the action space. This is the architectural inversion that separates Generation 1 prompt engineers from Generation 3 harness engineers. The prompt tells the agent what to do. The harness determines what the agent is even capable of doing. And here is what that distinction means for you. There are 3 distinct generations of AI engineering practice. And understanding where the boundary between them sits will change how you design every agent system you touch from this point forward. Let me be specific about what you will walk away with, because vague knowledge is not useful when you are trying to ship a production agent. First, you will have a working CLAUDE.md file. Not a template you copied from a blog post, but a structured document you understand at every line, because you know what layer it operates at and why each section exists. Second, you will have a scoped AGENTS.md file. This is the document that constrains your agent's world, the repositories it can see, the tools it can call, the operations it is explicitly forbidden from taking. Third, and this is the one most engineers skip, you will have a mental model for harness layer thinking. That means when something goes wrong with an agent, you will know immediately whether the failure lies in the prompt, the context, or the harness, and you will fix the right layer in spending 3 days rewriting instructions that were never the actual problem. These are not just concepts. They are deliverables. Files you can open, version control, and hand to a teammate. But here is what makes these tools dangerous without the right foundation. Most developers are writing CLAUDE.md files as if they are just fancy prompts, and that category error is exactly what causes the failures we opened with. To understand why the tools you are about to build matter, you need to see where they fit in the evolution of the field. AI engineering did not arrive fully formed. It went through 3 distinct generations, each one solving a problem that the previous generation created. Generation 1, prompt engineering. You write better instructions. You get better outputs, sometimes. But the more complex the task, the more the prompt buckles under its own weight. Engineers move to Generation 2, context engineering. You stop trying to fit everything into the prompt and start managing what information the model sees at inference time. Retrieval systems, memory layers, structured context windows. That buys you more capability. But it still does not solve the control problem. An agent with rich context and a great prompt is still an agent you cannot trust with right access to production. That is what Generation 3, harness engineering, finally addresses. And here is the thing that should concern you. The majority of the development teams building AI agents right now are operating entirely in Generation 1. They are solving a Generation 3 problem with Generation 1 tools. In the next chapter, we are going to draw the exact boundary lines between all 3 generations. And the moment you see where those lines are, you will never look at a prompt the same way again. Let's orient ourselves historically. In 2022, when GPT-3 and ChatGPT models hit mainstream adoption, the core insight was deceptively simple. The quality of your output depends on the quality of your input instruction. That insight spawned an entire discipline, prompt engineering. At its core, prompt engineering means crafting natural language instructions that steer a model toward a desired output in a single interaction. You write better words, you get better results. Teams started building prompt libraries, hiring prompt engineers, and publishing frameworks like Chain of Thought and Few-Shot prompting. And it worked. For its time, the 2022 inflection point was real. Models went from producing garbage to producing genuinely useful outputs simply by changing how you asked. But here is the thing nobody said out loud at the time. Every single technique assumed the entire job fits inside one turn. One input, one output, done. That assumption is about to collapse, and the next scene shows exactly how. Here is the structural ceiling nobody wanted to admit. Prompt engineering is built on one silent assumption. The model is stateless, and the task fits in one shot. You send a message, the model responds, the interaction ends. There is no memory of what happened before. There is no concept of step 2. Now ask yourself, what happens when you give an AI agent a real software task? Something like, refactor this module, run the tests, check the build passes, and if it fails, diagnose and fix the root cause. That is not one turn. That is 4 or 5 turns minimum, each dependent on the output of the last. And the model has no idea what happened in step 1 when it is working on step 3. Prompt engineering gives you a better steering wheel, but it does not give you a car that can drive itself across town. You are still sitting in the driver's seat for every single turn. The moment you let go, the moment the agent acts autonomously over time, prompt engineering has nothing left to offer. And that exact gap, is what forced the next generation into existence. By 2024, the field had acknowledged the stateless problem and proposed a solution. Stop optimizing the instruction. Start engineering the entire context window. This is context engineering. Instead of asking how do I phrase this better, you ask what information should the model have access to right now, and how do I structure it? That means injecting retrieved documents via RAG, injecting conversation history, injecting tool call results, injecting user-specific memory. The context window becomes a carefully designed information payload, not a question. Compare these two generations side by side. Prompt engineering controls what you say. Context engineering controls what the model knows. That is a meaningful upgrade. Andrej Karpathy's viral post in early 2024 crystallized this shift. He argued that context engineering would replace prompt engineering as the primary AI skill. And for many RAG-based applications, he was right. The context window went from being treated as a text box to being treated as a first-class engineering artifact. But, and this is critical, the word engineering in context engineering is still doing a lot of heavy lifting, and we are about to see where it runs out. So if context engineering is so much better, why are we here talking about a third generation? Because of a problem that richer context cannot solve. And it is a governance problem, not an information problem. Think about what an autonomous agent actually needs to operate safely and correctly in your production codebase. It needs to know what files it is allowed to touch. It needs to know that it must never push directly to main. It needs to know your team's naming conventions, your branching strategy, your test coverage requirements. None of that is a knowledge retrieval problem. Your RAG system can inject every doc in your Confluence, and the agent still won't know whether it is allowed to open a pull request or just create a draft. Context engineering tells the model what the world looks like. It does not tell the model what it is allowed to do in that world. And as agents get more capable and more autonomous, that distinction between information and governance becomes the most important architectural decision you can make. That unresolved gap is exactly what harness engineering was invented to close. Now we arrive at the third generation. And the word harness is doing something very precise here. It is not a metaphor for prompts, and it is not a synonym for context. It is borrowed deliberately from software testing and from equestrian tradition alike. A harness holds, directs, and constrains without replacing the power of what it controls. Martin Fowler, in his 2025 notes on AI-assisted development, described the harness as the scaffolding of intent that surrounds an agent, defining not what it should say but what it may do. OpenAI's systems documentation refers to the same concept as the agent's operating envelope, the structured environment of permissions, tool access, and behavioral guardrails that shapes every action the model takes. Red Hat's enterprise AI team calls it the agent control layer, the boundary between what the LLM can theoretically do and what your organization has decided it is allowed to do in practice. 3 different organizations, 3 different vocabularies, 1 convergent idea. There is a layer above context and above prompts, and that layer is what engineers need to build in 2026. The harness is not what you say to the AI. The harness is the world the AI operates inside. Let's make this concrete with a full 3-generation comparison, because this table is the core mental model you will carry into every AI engineering decision you make from here on. Generation 1, prompt engineering. You control the instruction text. It operates at the language layer. It fails when tasks span multiple turns. Generation 2, context engineering. You control what information the model has. It operates at the information layer. It fails when the agent needs governance, not just knowledge. Generation 3, harness engineering. You control the environment the agent acts inside, its tool permissions, its scope constraints, its project conventions. its escalation rules. It operates at the autonomy layer, its failure mode, and yes, it has, which we will get to, is over-constraint, not under constraint. Notice the pattern. Each generation moved one level deeper. From language to information to environment, each generation solved the failure mode of the previous one. And each generation introduced a new surface for engineering skill. Harness engineering is not replacing prompt engineering and context engineering. It is completing them. Your prompts still matter. Your context still matters. But without a harness, you are handing the wheel to an agent that has no concept of the road rules. In the next chapter, we dissect exactly what a harness is physically made of. So we've established that harness engineering is a generational leap beyond prompt and context engineering. But what actually is a harness made of? Not philosophically, structurally. Every production-grade agent harness, whether you're running Claude Code, OpenAI Codex, or a custom agentic pipeline, resolves down to exactly 4 structural pillars. First, constraints, the hard rules that the agent cannot violate under any circumstance, like never delete a production database record. Second, permissions, the explicit allow list of tools, APIs, and file paths the agent is authorized to touch. Third, project conventions, the shared engineering standards your team already uses, like naming schemes, commit message formats, and test coverage thresholds. And fourth, persistent memory artifacts, the durable, version-controlled files that carry these rules across every session, every new context window, every agent restart. Together, these 4 pillars define the operating envelope. The agent doesn't guess what's acceptable, it reads the harness. But here's where it gets interesting. Most teams only ever define 1 or 2 of these pillars, and that's precisely where agent failures originate. Now that we have the 4 pillars, let's talk about where they actually live in your repository. Because a harness isn't abstract, it's a text file sitting right next to your source code. In the Claude Code ecosystem, is materialized as CLAUDE.md. In the OpenAI agent ecosystem, it's AGENTS.md. These aren't configuration files in the traditional DevOps sense. They're not env files. They're not YAML manifests for a deployment pipeline. They are instruction layer documents that the agent reads before it touches a single line of your code. Think of CLAUDE.md as the onboarding document you'd hand to a senior contractor on day 1. Except this contractor reads it perfectly, every single time, and never forgets it mid-task. The critical insight here is that these files are the harness materialized as plain text in your repository. They travel with your code through Git, they're reviewable in pull requests, they're diffable, they're auditable. That's not a coincidence, that's intentional harness design. And in just a moment, we're going to crack open the internal anatomy of CLAUDE.md and see exactly what needs to be inside it. Let's get inside CLAUDE.md. An effective CLAUDE.md is not a wall of prose. It has a deliberate internal structure with 4 required sections, and skipping any one of them predictably breaks the agent's behavior in a specific way. Section 1 is the project overview, 2 to 4 sentences maximum, telling the agent what this codebase does, what language stack it uses, and what the deployment target is. This is not documentation for humans, it's domain grounding for the agent. Section 2 is coding conventions, explicit enumerated rules. Not follow P8, that's useless. Instead, all Python functions must type annotations. No f-strings in logging statements. Max function length is 40 lines. Section 3 is forbidden operations, the hard constraint list. Never run migrations without explicit human approval. Never commit directly to main. Never call external APIs in unit tests. Section 4 is escalation triggers, the conditions under which the agent must stop autonomous execution and surface a decision to a human. This is the section most teams omit entirely, and it's the one that causes the most catastrophic failures. The agent without escalation triggers is an agent that will make a judgment call when it shouldn't, and you won't find out until the damage is done. Theory is clean. Reality is messy. Let me show you exactly what the difference between a good and a bad CLAUDE.md entry looks like in practice, because this is where most teams fail, and they don't even know it. Take the convention around database migrations. A bad entry reads, "Be careful with database changes." That is not a harness instruction. That is hope. The agent will interpret it charitably and proceed. A good entry reads, "Never generate or execute database migration files unless the user explicitly types the phrase approve migration in their message." If a migration is required to complete a task, stop, output the migration file as a code block, and wait. See the difference? The bad version relies on the agent's judgment. The good version eliminates judgment entirely. It replaces ambiguity with a deterministic protocol. Here's the core principle. Vague harness instructions produce exactly the same failure profile as no harness at all. The agent doesn't fail loudly. It fails quietly, confidently, and completely. It does what it thinks you meant, not what you needed. Every single entry in your CLAUDE.md should pass this test. Can a new agent instance with 0 prior context Follow this instruction without making a single interpretive choice. If the answer is no, rewrite it. And that test, we'll apply it live in the very next chapter. Now let's cross the aisle to the OpenAI ecosystem. If CLAUDE.md is the harness artifact for Anthropic's Claude Code, then AGENTS.md is its counterpart for OpenAI Codex and the broader OpenAI agent runtime. But AGENTS.md has a different structural emphasis, and an understanding that difference matters enormously if you're operating in a multi-agent or mixed vendor environment. Where CLAUDE.md centers on behavioral constraints and coding convention, AGENTS.md is more explicitly focused on three things: scope boundaries, tool access permissions, and task delegation rules. Scope boundaries answer the question: what parts of this repository is this agent allowed to reason about and modify? Tool access permissions answer: which function calling tools, which APIs, which shell commands is this agent authorized to invoke? And task delegation rules answer: when this agent receives a task that falls outside its scope, who does it hand off to and how? This last one is unique. AGENTS.md explicitly supports multi-agent orchestration patterns, where different agents own different domains of your codebase. It's a harness designed for agent teams, not just individual agents. But does that make it better than CLAUDE.md? That depends entirely on your stack, and the comparison table coming up will make that decision concrete. Let's put CLAUDE.md and AGENTS.md side to side across 6 concrete dimensions, because the choice between them, or the decision to maintain both, is one of the most practical engineering decisions you'll make when standing up an agentic system in 2026. On syntax, CLAUDE.md is pure markdown prose with structured sections, readable by any team member. AGENTS.md supports a more schema-driven format with explicit key-value declarations for tool permission. On scope, CLAUDE.md applies globally to the repository by default. AGENTS.md supports directory-level scoping, meaning you can have different agent rules for your backend and infraland. On declarations, CLAUDE.md describes tools implicitly through convention text. AGENTS.md declares tools explicitly, making the allow list machine parsable. On memory model, both persist across sessions as files, but AGENTS.md has tighter integration with OpenAI's stateful thread model. On escalation, CLAUDE.md requires you to write escalation triggers manually in natural language. AGENTS.md has a structured escalation declaration syntax. And on portability, this is the key tension. CLAUDE.md is vendor-specific to Anthropic. AGENTS.md is vendor-specific to OpenAI. Neither is portable out of the box. And that, the portability problem, is exactly why the next chapter exists. We're going to write a production CLAUDE.md from scratch, and you'll see every one of these design decisions made in real time. Before you write a single line of CLAUDE.md, you need to pick the right project, and most engineers get this wrong. They reach for their largest, most critical codebase first, thinking that's where the AI will deliver the most value. That instinct will burn you. Your first harness should be a project that is bounded, has at least partial test coverage, and has a deployment pipeline you fully understand. Think of it like fitting a harness on a horse for the first time. You do not start with a wild stallion on race day. The 4 criteria you must evaluate are codebase size and modularity, existing test coverage percentage, deployment pipeline complexity, and your team's current AI usage maturity. A monorepo with 0 tests and a hand-rolled deploy script is not your first candidate. A standalone microservice with 80% coverage and a standard CI pipeline. That is your starting point. The discipline of choosing correctly here will save you 3 weeks of debugging agent behavior in the wrong environment. And here is the thing nobody tells you. The right project is almost never the one your manager will suggest. Now let's look at the actual scaffold, the blank CLAUDE.md template you will use as your starting point for every project. This is not a prompt. Do not think of it as a prompt. Think of it as a constitution. It has 5 mandatory sections and each one serves a distinct architectural purpose. The first section is project context, a 3 to 5 sentence description of what this codebase does and what it does not do. The second section is constraints, the hard rules the agent cannot break under any circumstance. Third is conventions, the softer style and process rules the team has agreed on. Fourth is escalation triggers, the explicit list of situations where the agent must stop and ask rather than proceed. Fifth is tool permissions, which CLI tools, APIs, and file system paths the agent is allowed to touch. Noticing, there is no section called instructions or prompt. Those words do not appear in a harness. You are not instructing a chatbot. You are configuring a system. The blank scaffold you see here is what every engineer on your team should commit to their repo on day 1, before a single agent task is ever run. Let's start filling it in. Let's write the constraints section live. The single most common mistake engineers make here is writing constraints that sound strict, but are actually permissive when the agent interprets them literally. Consider this example. You write "do not delete important files." The agent has no definition of important. It will proceed to delete what it judges unimportant, and it will be wrong. Every constraint must name the exact pattern, directory, or operation class it protects. Watch the difference. Instead of "not modify CI configuration," you write "never modify file matching the path workflow file in makefile, dockerfile, or docker compose YML." Instead of "be careful with database migrations, never delete, rename, or modify any file in DB migrate. New migrations may only be created, never altered." Notice the pattern. Everything specifies the file path or glob, the exact operation class being forbidden, rename, modify, and 0 exceptions are granted. The moment you add the phrase "unless necessary," you have invalidated the constraint entirely. The agent will always find a reason something is necessary. Phrasing precision here is the difference between a harness and a suggestion box. Now the conventions section. This is where your team's collective knowledge gets encoded, the stuff that lives in senior engineers' heads and never makes it into the README. Start with 3 categories: file organization, naming rules, and test requirements. For file organization, you might write, every new module must have a co-located test file in the same directory with the suffix .spec.tsis. This single line eliminates the common source of drifting test coverage in AI-assisted development. For naming rules, encode things like all database column names use snake case, all TypeScript interfaces are prefixed with a capital I, all React components use cal case. These seem obvious to your team. They are completely opaque to an agent operating without this context. For import order, instead of hoping the agent guesses, write it explicitly. Built-in node modules first, then third-party packages, then internal aliases beginning with the @ symbol, then relative paths. Finally, naming. Feature/ticket number/short description. That pattern. Hard-coded. The agent should never guess what branch to create. It should follow the exact pattern you have specified here. What you're really doing is converting implicit team knowledge into explicit machine-readable law. The escalation triggers section is arguably the most important part of your entire harness, and it is the one most teams skip entirely. Here is why that is catastrophic. Without explicit escalation triggers, your agent will make a decision at every ambiguous fork in the road. It will pick a direction, proceed confidently for 200 lines of code, and surface a result that is technically coherent but completely wrong for your use case. You find out 30 minutes later. Escalation triggers prevent this by defining the exact conditions under which the agent must surface a question rather than make an assumption. Write them as conditional statements. If the agent cannot identify a unique test to run for the change it made, it must stop and ask. If modifying a file would touch more than 3 modules, it must stop and ask. If a new external API call is required that is not already present in the codebase, it must stop and ask. If the task requires inferring a business rule that is not documented in code or comments, it must stop and ask. The key phrase in every trigger is "must stop and ask." Not "should consider asking," not "may escalate." The agent has to treat these as hard exits. This section right, and you convert your agent from an autonomous agent that surprises you into a collaborative system that keeps you informed. And that transition, from surprise to collaboration, is precisely what separates a toy demo from a production tool. Next up, we test whether any of this actually works. You have written your harness. Now you need to red team it before you trust it. This is the step that separates engineers who deploy reliable AI systems from engineers who deploy time bombs. The harness testing loop works like this. You design a set of deliberately adversarial tasks. Tasks that sit right on the boundary of every constraint and trigger you wrote. You are not trying to make the agent succeed. You are trying to make it fail so that you can find the gaps now instead of in production. For your constraints section, give the agent a task that would naturally require it to touch a forbidden file path. If it proceeds without escalating, your constraint phrasing is too weak. Go back and tighten it. For your conventions section, give it a task that involves creating a new module and check whether the co-located test file was created, the import order is correct, and the branch name follows the pattern. For your escalation triggers, give it a task with deliberate ambiguity, 2 valid ways to implement the feature, and verify that it stops and asks rather than picking one silently. Run at least 3 adversarial tasks per section. Document every failure. Each failure is not a bug in the agent. It is a gap in your harness specification. Treat it as such, fix the harness, and run the adversarial task again. This loop typically takes 2 to 4 hours on a first harness. That investment pays back within the first week of production use. The last thing you need to understand before we move to real-world examples that your CLAUDE.md is not a document you write once. It is a living team artifact. It needs to be versioned, reviewed, and updated on a regular cadence. Commit it to Git from day one. Every change to it should be a pull request with a clear description of what behavior and why. When a new engineer joins the team and runs an agent task, their results are your first signal that something in the harness has become ambiguous or outdated. Review the harness with them, not as a correction, but as a calibration session. Set a recurring team review every 2 weeks for the first 3 months. Look at the Git log of CLAUDE.md the same way you look at the Git log of your core business logic, with the same level of scrutiny. Over time, 2 types of updates will drive most of your harness iterations. New capabilities added to your codebase that require new constraints and agent behaviors that consistently drift in an unexpected direction. Drift is your most reliable signal that a rule is underspecified. And here is the concept that ties all of this together. Your harness evolves with your codebase, not against it. The next chapter shows you what a mature, battle-tested harness looks like in a real company at scale. We're going inside Stripe's engineering workflow, and the gap between what you'll see there and what most teams are running today will surprise you. Let's talk about a number that stopped most engineers cold when they first heard it. 1,300 AI-generated pull requests merged per week at Stripe. Not opened, merged. That means reviewed, tested and shipped into a payments infrastructure that processes hundreds of billions of dollars annually. The question is not whether AI agents can write code. We already know they can. The real question is, what harness-level controls make it safe to trust that volume of machine-generated changes without a single rogue PR taking down card processing for millions of merchants? Stripe's approach did not start with prompt tuning. It started with workflow architecture. Each agent task was scoped to a single bounded domain, one service, one module boundary, one contract. Agents were never allowed to cross service lines autonomously. Every PR was tagged with its originating agent session ID, making audit trails automatic. Linting and static analysis gates ran before any human reviewer ever saw the diff. The result: human reviewers spent time on logic, not on catching formatting regressions or import mismatches. But here is what most people miss about this system. The harness was not built in a day, and it was not built by AI researchers. It was built by platform engineers who understood failure modes first. We are about to extract exactly what made it work. Now let's extract the 3 lessons from Stripe's model that you apply regardless of whether your stack is Claude, Copilot, or something else entirely. Lesson 1. Scope isolation is not a constraint on the agent, it is a constraint on blast radius. When an agent can only touch one bounded context, a bad output cannot cascade. The agent failing loudly inside one module is infinite better than a silent regression threading through 5 services. Lesson 2. Mandatory automated test gates before human review is not about distrust. It is about respect for human attention. Human reviewers are expensive and cognitively limited. Routing machine generated through human eyes before basic gates pass is a harness design failure. Full stop. The gate is what makes human review meaningful. Lesson 3. And this one surprises most teams. The agent-authored change summary is itself a harness output. When the agent is required to produce a structured explanation of what it changed and why, you get 2 things simultaneously: a review artifact for humans and a behavioral signal about the agent's own confidence in the change. An agent that produces a vague or contradictory summary is signaling something worth examining before merge. These 3 patterns, scope isolation, gate-first review, and structured agent output, are the transferable core of what Stripe built, and they map directly onto the CLAUDE.md structure you built in the previous chapter. But knowing the patterns is only half the problem. The harder half is knowing when your harness is miscalibrated. And that is exactly where we are going next. Stripe is not the only organization publishing harness-level thinking. The awesome Harness Engineering repository on GitHub has become a community-curated catalog of patterns that practitioners across the industry have documented, tested, and open-sourced. Think of it as the equivalent of Awesome React or Awesome Go, but for the discipline of constraining, shaping, and governing AI agents in production engineering environments. The most reusable patterns in the catalog cluster around 3 categories. First, context delivery patterns, standardized ways to inject project-specific knowledge into an agent session without blunt text window. This includes file reference injection, workspace summary templates, and dependency graph snapshots. Second, output contract patterns, schemas that define what a validate output looks like before the agent is ever invoked. If the agent's output does not conform to the schema, it never leaves the harness. Third, escalation patterns, define triggers that cause the agent to pause and surface a human decision point rather than proceeding autonomously. These are not prompt hacks. They are structural patterns implemented at the tooling or workflow layer. What makes the awesome Harness Engineering catalog valuable is not any single pattern. It is the taxonomy. Once you can name the category of problem you have, you can find or build the right solution. And the patterns are tool agnostic, Whether you are using Claude Code, Cursor, or a custom 8-agent pipeline, the harness pattern category applies. But which pattern to reach for requires first recognizing which failure mode you are in. And there are exactly two, with very different symptoms. Here is where most teams go wrong. And they go wrong in one of exactly two directions. The first failure mode is over-constraining the agent. You have locked down every file path, restricted every tool call, required human approval for every single output, and wrapped the agent in so many rules that it produces nothing useful without constant hand-holding. The diagnostic signal. Your agents are technically running. Your engineers report that it is faster to just write the code themselves. The harness came a straitjacket. The second failure mode is the opposite and far more dangerous. Under-constraining the agent. No output contract, no scope boundary, no escalation trigger. The agent has access to everything and reports to nothing. The diagnostic signal here is subtler. Things look fine for weeks, and then a single agent's session silently refactors a shared utility that 12 other services depend on, and you find out in production. The balance point between these two failure modes is not a fixed setting. It is a calibration that depends on your codebase maturity, your test coverage density, and the reversibility of the actions your agent can take. Low test coverage plus irreversible actions equals a harness that must lean heavily toward constraint. High coverage plus easily reverted changes equals room to loosen the harness and let the agent move faster. The key insight, harness calibration, is not a one-time decision. It is an ongoing engineering discipline. And that realization is what is driving the emergence of an entirely new team role, which we are about to define. What Stripe built, what the awesome harness engineering catalog documents, and what the two failure modes unavoidable is a single conclusion. Harness engineering is not something you can bolt onto an existing role. It is emerging as a distinct team discipline with its own skill stack, its own ownership boundaries, and its own relationship to production risk. Let's be precise about what that skill stack actually looks like. At the base, you need deep platform and infrastructure knowledge, the same foundation that a senior platform engineer carries. You need to understand how CI/CD pipelines, at the mechanism level, how service boundaries are enforced, and how rollback systems operate. One layer up sits workflow architecture, the ability to design multi-step agent pipelines with explicit state transitions, failure modes, and human escalation points. This is closer distributed systems design than to software development in the traditional sense. Above that sits harness-specific knowledge, output contract design, context window budget management, isolation patterns, and behavioral monitoring of agent outputs over time. And at the top, governance and policy. Who owns the harness? Who has authority to loosen a constraint? How does a harness change get reviewed before it reaches production? Notice what is conspicuously absent from this stack. Prompt writing. Not because prompts are irrelevant, but because prompt writing is a subtask within the governance layer, not the discipline itself. Harness engineering sits closer to platform engineering than to AI research, and that is not an accident. The teams that ship AI at scale treat it as infrastructure, not magic. The final chapter will show you exactly how to start building this discipline inside your own organization. And the first move is simpler than you think. Let's make this actionable. Knowing that harness engineering matters is useless without a concrete path to actually doing it. So here is your 30-day roadmap. Not a theory exercise, a real implementation plan. Week 1. Pick one live project, write your first CLAUDE.md. Nothing fancy, just document the repo structure, the coding conventions, and the 3 decisions the agent should never make autonomously. That alone will change how your agent behaves. Week 2. Stress test that harness. Run the same task 5 times with different phrasings. If the agent's output variance is high, your harness is underspecified. Tighten it. Week 3. Bring one teammate into the harness review. Harness engineering is a team discipline, not a solo craft. Week 4. Write an AGENTS.md alongside your CLAUDE.md and run a comparative experiment. See which file produces more consistent, audible outputs. By day 30, you will have a harness engineering practice, not just knowledge of one. But here is the part most engineers skip. The experiment in week 4 will reveal something surprising about how different agents read the same constraints differently. Now let's talk about where to go deeper. There are 3 primary sources that together give you a complete mental model of harness engineering. Each one covers a different angle. First, Martin Fowler's article on AI agents frames the architectural picture. Why autonomous agents require structural constraints, and how harness thinking maps onto well-established software design principles. Read this if you want the conceptual foundation. Second, the OpenAI blog post on AGENTS.md gives you the practitioner's view, the actual file format, the reasoning behind each section, and real examples from OpenAI's own internal agent workflows. This is the reference document you will return to repeatedly. Third, the Red Hat Developer Write-Up approaches harness engineering from an enterprise reliability lens, failure modes, observability gaps, and why harness discipline is especially critical in regulated or high-stakes environments. Together, these 3 documents cover theory, practice, and risk. And notice what none of them are. None of them are about writing better prompts. That gap, the silence around prompts, is itself the signal. The field has already moved. The only question now is whether your engineering practice moves with it. Let's consolidate everything this lecture has covered into 5 takeaways you can carry forward. 1. AI engineering has moved through 3 generations: prompt engineering, context engineering, and now harness engineering. And each transition was driven by a fundamental change in what the agent is being asked to do. 2. The hives in 2 files, CLAUDE.md for the repository level and AGENTS.md for the agent orchestration level. These are not documentation artifacts. They are executable constraints. 3. Stripe's production deployment is not a case study in a textbook. It is live validation that harness engineering works at enterprise scale right now. 4. Through failure modes, the agent that hallucinates because the harness is absent, and the agent that is paralyzed because the harness is overspecified, are equally dangerous and equally common. 5. Harness engineering is a team discipline. A harness authored by one engineer and never reviewed is a single point of failure. The moment you treat CLAUDE.md as a shared artifact with code review, you have made the shift. Now, those 5 points describe where we are. But what they don't tell you is what happens when agents become genuinely more capable than they are today. That is where the next insight lands. Here is the paradigm-level implication, the one that changes how you think about your entire role as an engineer. As AI agents become more capable, the instinct is to focus on the model, better outputs. That instinct is wrong. A more capable agent operating inside a poorly designed harness is not safer, it is faster at being wrong at a larger scale with greater confidence. The harness is where your engineering judgment lives now, not in the prompt you write, not in the model you select, in the structural constraints that define what the agent can see, what it is allowed to decide, and when it must stop and ask. That is where competitive advantage gets built. Organizations that treat harness design as a first-class engineering discipline will move faster, with fewer catastrophic failures, than organizations still arguing about which prompt template to use. Call to action is this: go first, CLAUDE.md today. Not this week, today. The 30-day roadmap starts at day 1, and day 1. Engineers who build harness engineering practices in 25 will be the ones setting the standards that everyone else follows in 27. Harness is the leverage point. Everything else is just configuration.